Yes, Zara, Assalamu alaikum.
Assalamu alaikum, ma'am.
Walaikum salam. So, yes, Zara, in the last class, we just stopped at this point, gravitational potential energy. So, from spring mass system, let's continue. Okay. So, see, basically, spring mass system is just one unique system that is given to you, where a spring is connected to a mass. And see, this will come again in your simple harmonic motion. And a formula from simple harmonic motion will be used. So, because we haven't done that chapter, so I'll be just giving you an overview about what will come next. See, you have a spring and a mass connected. Now, whenever you have any system at its resting position means its starting position. So, at its resting position, this means its starting position. At its starting position means this is known as the mean position. Means no force is applied by nature, whatever is the position of the body. That is termed as mean position. Now, here for a spring mass system, everything will be taken with respect to this mean position. Everything will be taken with respect to this mean position. Let's say I have a spring. I have connected it to one end and I have elongated the spring. So whatever is its displacement from the mean position, okay, whatever is its displacement coming from the mean position, that is what we refer to as the x. Basically, we use the symbol x, that is enough for it, okay, displacement from the mean position. That is your starting position or what we call as the resting position. So let's say if I've elongated the spring, so this x will be its direction. This x will be the direction of the spring, direction of the displacement. Similarly, what if I compress the spring? If I compress the spring, again, there will be a displacement from the mean position on the opposite side. So this separation from the mean position, this is what is known as the displacement from the mean position. Displacement from the mean position means you are taking the separation from the mean position. That is how much has it been displaced from its original resting point. Let's say if it was the mean position was here, it has expanded to here, it has narrowed down to here. Like this, different points we'll see. So here the force that is actually pulling it or pushing it inside, that is known as the external force. And any force that acts in the system to bring it back to its mean position, that is known as the restoring force. See what all things we have. I'll repeat it also. The force that is required to pull or push your mass, that force is known as the external force. And whenever the object has been displaced from its mean position, a resting force will automatically act so as to bring the body back to its mean position. This force is known as the restoring force. Now, if restoring force is always directed towards the mean position, its direction is towards the mean position. How? See, this is the block mass M, this is the mean position. So it will try to bring it back to the mean position. If it is here, it will try to bring it back to the mean position. So restoring force's direction isn't fixed, but this is fixed that it will be directed towards the mean position. So this line you can forget, direction of restoring force. This will just confuse you. Here, see, remember, this external force that I'm referring to, this is always proportional to the displacement. This is the displacement from the mean position. This is the displacement from the mean position. While this is the external force. This is always proportional to it. Now, in order to apply it, in order to use it, we use another formula for it, that is F is equal to minus Kx. Means when you remove the proportionality sign, you get this constant. See, what are the terms here? F is the applied force. F is the applied force. Minus sign tells that it is directed towards mean position. Directed towards the mean position. K is known as the spring constant here. This is termed as the spring constant, while X is the displacement from the mean position. Displacement from the mean position. So this is actually a whole concept from your SHM, but I just needed this formula F is equal to Kx. So I can't just directly use this formula F is equal to Kx because you'll have no idea what is it. So a little background of it I have told you. All these things will come again in your chapter SHM. So I'll just quickly repeat what is this and then we'll see the derivation. And if there's any trouble, let me see. You have a spring which is connected to a mass, a block of mass m. Now, this position, when the block is resting, there is no force acting onto it, nothing. It is as it is on itself in its natural state. It is known as the resting state, which is the starting position. We call as the mean position. All these terms are from your simple harmonic motion. If I elongate it to here, so there will be a displacement along the mean position, or if I compress it further, so there will be a displacement. So if I apply a greater force, a greater displacement will be there. If I apply a very lesser force, a lesser displacement will be there. I can say external force is directly proportional to the displacement from the mean position. So in short, when you replace the proportionality sign with a constant, this constant is the spring constant that will be given to you. And all these things will come again in your SSM chapter. Till here, am I clear,
I'm
Zara?
a little confused in restoring force because I did understand that what displacement means and the external force, but I am confused in restoring force.
Restoring. Okay, I'll tell you. See, whenever in nature anything is disturbed from its original state, nature has the mechanism to bring it back to its original state. So external force is any force that is out of the system, like let's say I am there and I am pulling the block, so that becomes the external force. But since I have disturbed the system, the resting position where it was the stable, it was at its mean basic position, it was this, I have disturbed it. The external force has disturbed it. Automatically, there will be a restoring force developed. If a body is rotating, so a restoring torque will be developed. Torque is basically the rotational force. So restoring torque or restoring force is developed that tries to bring the body back to its original state so that it can again be stable. There is no disturbance. We have disturbed it. External force has disturbed it. So what will the nature try to do? It will try to bring the body back to its relaxed state where it was originally present at its starting position, which is its mean position. Now, when you have the block extended like this, you have extended it, restoring force will be towards the mean position so that it can bring it back. When you have compressed it so much, so restoring force will act towards the mean position to elongate it back to its original length. So restoring force is developed in response to the external force. You must have done action reaction of Newton's law. So as a response of this external force, a restoring force is developed so that your system can be brought back to its original state where it was at its mean, at its resting position, and no external force was coming into the system and disturbing the system's equilibrium. Got it?
Yes, ma'am.
Okay. Write down this till here, then I'll discuss the derivation of the spring. Okay.
Should I draw the figure or can I understand it without the figure?
I think you should write everything because we have a chapter SHM, no? So there it will be helpful for you. Okay.
Ma'am, I'm not gonna have a class on Friday,
Yeah, we'll have 1 hour
but
class.
the class today. Okay, so it's gonna be a 1 hour class.
Yeah, see, 3 hours per week is your schedule. We
Oh,
we were supposed to have 1.5, 1.5. So since we are not able to have that, so 1 hour, 1 hour, 1 hour. That's better.
yes,
Or
ma'am.
any day you are unavailable or anything, just inform us before. That can be adjusted later on. Okay. Okay. Ma'am.
Ma'am. Ma'am, what did you write on the M block in the second figure?
Where M, F external.
Oh, external force. Okay, ma'am. Done, ma'am. Done, ma'am.
All right. Now see, let's say we have a spring and a mass is connected and this is its mean position from x equal to 0. Until x equal to x, I have stretched it. I have elongated it using some external force. Now here, force is equal to kx if I take the magnitude from the spring mass system. All right, now F is equal to kx. Now work done is equal to, see, when you have the variable force, I discussed with you that we use F dot dx rather than F dot, just F dot dx. We use F dot dx integral, not F dot x. So from 0 to x, we'll integrate. Now let's put the value of the work done. Work done is equal to force is kx
Why did
dx.
minus kx, ma'am?
F is equal to kx from here, this formula.
But it's not minus kx, right? I'm asking that.
Okay, you said talking about the minus sign. See, minus sign was for the direction. Taking
Oh,
the
okay.
magnitude, okay, because work, we are calculating work done, which is a scalar quantity. Okay,
Okay,
now
ma'am.
for work done, k, which is the constant, is taken out. Integral x dx from 0 to x is left. Yes, Zara, integral of x, what will it become? Okay, x to the power n becomes integration.
N minus.
That is differentiation. See, n plus 1 divided by n plus 1. Okay, so if you have x to the power, this is x only, that means x to the power 1 is there. So that means work done will be k x to the power 1, that is 1 plus 1 divided by 1 plus 1 from 0 to x. This is k x square by 2 from 0 to x. Okay, now what we do, we put the upper limit in place of this
And
x
we must.
minus. So work done will be k by 2 x square minus 0 square. So this is equal to, work done is equal to half k x square. Now see, work done is stored in the form of potential energy. So potential energy of a spring, this derivation comes in the exam, that is half k x square. So for the derivation, you need not mention the entire thing which you have written. Just mention this in one line. This, why are you using f is equal to kx in one line? That's it. Okay. Till here it's clear?
Yes.
Okay. So now we'll do conservation of mechanical energy. Write this derivation. Then let's.
Ma'am, can we do integration and differentiation once more in the next class? Because I'm still very confused somehow.
Okay, fine. On Friday, let's complete it.
Okay. Done, ma'am. Done, ma'am.
Okay. So see, conservation of energy. We already talked about conservative and non-conservative forces. So when you have non-conservative, the term conservative only tells you that something is being conserved. Non-conservative means the energy is not getting conserved, in the sense some amount of energy is getting dissipated as heat. Best example is friction force. This we have already talked about. So for the perfect conservation of energy, only conservative forces should be there, because non-conservative are dissipative. So these things we have already discussed. I am just summarizing it here under the category of conservation of energy. Now, when we talk about the total energy, mechanical energy, as I told you, that is the sum of kinetic and potential, kinetic energy plus potential energy. So this means that whatever is the initial kinetic energy plus the initial potential energy is equal to final kinetic energy plus the final potential energy. Okay, initial kinetic plus initial potential is final kinetic plus final potential. So in short, you can even say the change in the kinetic energy plus the change in the potential energy is zero. Means this is your total kinetic energy.
Initial plus final, and the other one is my total potential energy, initial plus final.
Initial plus final, yes. This is initial, all the initial energies, all the final energies, they are equal. Then only we'll say conserved. It's like if 4 joules of potential energy and 2 joules of kinetic energy were there. This should still be equal to 6 joule anyways. It means whatever is the distribution. Let's say 1 plus 5 joules. Okay, anyways, it should be equal. So that's why we take the sum of all of them. So this is the total kinetic energy, and this is the total potential energy. Now, why kinetic and potential only? If we know work done is equal to change in kinetic energy, okay, which is equal to mgh for potential energy, and we know work done is in fact it's better if you remember it like this way. Why are their changes equal to each other? Basically the entire kinetic energy gets stored in the form of potential energy also. Let's say change in kinetic energy is equal to work done according to work energy theorem. Similarly, I discussed with you that potential energy is also stored, work done is also stored in the form of potential energy because of work potential energy theorem. Work potential
Energy
And
theory.
yes. So if work done is equal to kinetic, same work done is equal to potential. So we can directly say change in kinetic is equal to change in
Potential.
potential.
Then the kinetic energy is equal to work done.
What?
So this is the only proof we'll need for the whole derivation.
This is not a derivation. It's just that, see, how can we say that kinetic energy is getting converted to potential? Reason is that kinetic can convert, see, reason is kinetic energy can be converted into work done, which can be converted into potential. So we can say kinetic energy can be converted into the form of potential. Like I'll give you an example. If a ball is there at a height of a certain tower, let's say this is our tower and a ball is here. So when the ball is at height, here potential energy is there, mgh. And since it is at rest, kinetic energy is zero. As soon as this ball is dropped, when the ball comes, I'll give this example. We'll discuss this also. This is there in your syllabus also. But when the ball is moving with its velocity and coming to the ground, here kinetic energy is acting half mv square, potential is zero. So what has happened? Basically, entire potential energy got converted into the kinetic energy. So how can we prove this? Like how is it happening? It is occurring because of a common medium through them, that is the work done. Now clear?
Yes.
Okay, so there is one more derivation part, but you write down this theory part, then one question we'll discuss. Okay, this will complete this topic.
Ma'am, what did you write after in your system under that?
Example, friction force.
Okay. Ma'am, kinetic energy plus potential energy is also equal to mechanical energy, right?
Yes. So we can say total mechanical energy is conserved. Basically, initial mechanical energy is equal to final mechanical energy. You're right.
Done, ma'am.
Okay. There is just one small question that comes. This often has been asked in the school exams because this question connects gravitation chapter also, kinematics also, and it's definitely a part of this chapter. So see, this says show that total energy of a freely falling body is conserved, which I was discussing with you. So here we are going to choose 2 points, initial point and the final point, and we'll see are the energies same or not. If it is same, it means it is conserved. If it is different, it means some of it has been dissipated in other form. So let's say we have a point A. At A point, this is the initial point, A point. Okay, it is at a height h. Now body is initially dropped. Okay, body is dropped from rest. In this case, if it is dropped from rest, the velocity is 0. Therefore, we can say kinetic energy is also 0 because no movement is there. It is dropped from rest, so no movement right now. But since it is at a certain height h, potential energy will be still there in our system. So when we talk about the potential energy that will act will be the gravitational potential energy. So at this point, no kinetic energy, but potential energy will be equal to mgh. So my LHS means total initial energy, kinetic initial plus potential initial. So kinetic initial is 0. This plus potential initial is mgh is equal to mgh. So this is my one side, initial side. Let's see finally. So finally, let's say this is the point B at which the body has been dropped. Now, when this is dropped to this point B, now the body was moving. Let's say at B point. Okay. So here the potential energy now is becoming 0 because the displacement is 0. As soon as it is touching the ground, the displacement is 0. So since displacement is tending to 0, therefore potential energy is 0. But what about the kinetic energy? Since it is moving and it is about to come at rest, kinetic energy right now will be there. That is half mv square. Now velocity we don't know. So let us calculate. See what will be the velocity. V, if I use the third equation, v square minus u square is equal to 2as. Third equation of uniform acceleration. Remember this equation, Zara?
Yes, ma'am.
Of uniform
Acceleration.
acceleration, yes. So v square I have to calculate. Initially it was at 0, 2. Now when it is freely falling, what's the acceleration which we use? Which type of acceleration? Freely falling body, acceleration due to gravity. G. Okay, G which is equal to 9.8 meter per second square. Remember? Is it clear?
Can we not take 10?
Right now I'm not putting the value. I'm just saying Z will take. This I was just writing to make you recall. And one more thing, Zara, in the questions, do not take the value of G as 10 unless stated. Sometimes you can lose marks. It depends on your teacher though, but this is a rounded off value, 10. Actually is 9.8. But it depends. Sometimes marks are given for that also. So height is h. So what is V square equal to? 2gh. Let's put the value of put V square in kinetic energy. So kinetic energy will be half m. What is V square? 2gh. 2 gets cancelled. This is mgh. So my RHS.
Is equal to LHS.
Yes, exactly. Because my RHS is final kinetic energy plus final potential. This is mgh plus 0, still mgh. So initial kinetic energy, we can say LHS is equal to RHS. Hence, energy is conserved. Got it?
Yes.
So this completes with work done was over, and this completes with energy also. Now we are left with power, and there is one more topic in this chapter, collision. So
Oh,
these two topics are just left. Okay, please write it to me.
ma'am, done. Ma'am, done. Done, ma'am.
Okay, see, now talking about the concept of power. So power is very easy. See, more importantly, you had to understand energy, and everything is related to your energy. Whenever you have the term rate term is there. Rate means something which changes with respect to time. This means change with respect to time. Okay, something that is changing with time. Like we say rate of change of velocity is acceleration because it is velocity divided by time. Or rate of change of displacement is velocity because it is displacement divided by time. So similarly, power is rate of doing work, means how much work is done in 1 second. Work done divided by time. Basically, this means how much of work done has been done. How many joules of energy has been spent in a duration of 1 second. So it's a scalar quantity. SI unit, we don't write it as, see, joules per second is there, but the actual unit is watt. WATT. So capital W is used to represent it. Now see, if you have a duration provided to you, if you have a duration in the sense time duration is there. Example, 4 seconds to 10 seconds like this. Okay, if you have a duration given, then what you can calculate for the average power change in the work done by the change in the time. Change in the work done means final work done minus initial work done by final time minus initial time. This you can use if you have the duration given. Instantaneous power means if I have a time instant with me. If I have a time instant present. For example, if I ask you to calculate the work done exactly at 4 seconds or exactly at 10 seconds, not 4 to 10 seconds, this becomes the duration. This is a time instant. So for instantaneous power, what do you do? For instantaneous power, differentiate work done with respect to time. dW over dt. In both the cases, you will get the answer in one line, though the actual formula is work done by time. Now see, different work done takes different form of shapes of different energy. Sometimes it can be kinetic energy, sometimes it can be potential energy. Whatever is it, you use the same formula. So for us, the power will be basically energy per unit time. Okay, so this makes it energy per unit time.
Right.
Okay, clear this part?
Yeah.
All right. Um, write it till here first, then I'll move further.
Ma'am, the triangle represents the difference, right?
Yes, yes. Triangle, see, when you have a triangle, this means a finite change. Finite change means a change that can be calculated using simple subtraction. Final minus initial. Whenever you see the symbol delta, delta x change in position, delta p change in power, delta with anything you can put, scalar, vector, anything. But when small d is there, this means this is infinite change, infinitesimally small change, infinite small change. So you differentiate in that case or integrate. Simple subtraction doesn't work.
Then, ma'am, please pull it down. Done, ma'am.
Okay. Zara, have you understood today's class? Everything properly?
Yes, ma'am. I did understand everything properly.
Okay. Zara, I'll stop here. Now, power, I think it will be 2